14 carats, I'm 14 carat, doing it up like Midas. Now you say I got a touch, so good.
Okay, so for here, they give us the following sequence: d sub n equals square root of n plus 3 minus square root of n. So we're supposed to find the limit, or show it diverges. Okay, so that's what we're doing for this problem. So first of all, what I'd like to do is put this in f of x form. So that just means replacing all the n's with x's, right? So we're going to have square root of x plus 3 minus square root of x. Okay, and then I like to rewrite things with exponents. So I'm going to write this. And the reason behind this is writing it in function form is because I'm going to take the first derivative to see if it's a decreasing function or an increasing function. Okay, because then we can prove things by the by the variety of theorems that we encountered in this section. So if we take the first derivative, this is going to be the 1/2 comes down in front, and then we have x plus 3 to the negative 1/2 now, and then minus 1/2 x to the negative 1/2. So in a different form, this would just read 1 over 2 times x plus 3 minus 1 over 2 times square root of x. Okay? So then, as we can kind of tell here, the denominator here on the first term is greater than the denominator here, right? Because we have this plus 3. So if the denominator is bigger and the numerators are the same, then we know that this number, this whole fraction, is going to be smaller than this fraction. Therefore, this whole thing, so this is smaller, small, and this is bigger, right? So a small number minus a bigger number is going to be negative, which is less than 0, right? So that means that for all x is greater than 0, then we're guaranteed that the first derivative, this f prime of x, is less than 0. So it's going to be decreasing. So the function f of x must be decreasing, which also means since we represented, or this function represents the sequence, that means that the sequence must also be decreasing. So function and sequence, dn, must be decreasing. Okay, so this is decreasing. And it's monotonic. Okay, so then now let's look at the sequence itself. So we have dn equals square root of n plus 3 minus square root of n. Okay, so for all n, then we have that dn is greater than 0, right? Because of this plus 3 here. That means that whatever we plug in for n, so even if you plug in a 0, then you're going to get a positive root 3. And if you plug in a 1, then you get something else that's positive. So because dn, so this is kind of like its lower bound, right? Remember that? So this is like our little m, okay? So because of this, so by theorem 6, I looked this up, on this is on page 550. You can look at it because I don't want to write the whole thing out. It guarantees that because our sequence, because d sub n is monotonic decreasing, right? We proved that with the first derivative part being negative, and dn has a lower bound, which we proved the second part here has a lower bound of 0, technically, of 0, then, our big then, limit as n goes to infinity of the sequence, limit of the sequence equals some big L exists. So we kind of did the first part. We definitely showed that it does not diverge because we said that a limit exists, and now we have to find the actual numerical limit. So don't worry though, because the second part is a lot simpler conceptually. So I'll continue on the next slide. So now our goal is to find this exact limit of n plus 3 minus square root of n plus 3 minus square root of n. So what I'm going to do here, I don't know if you might recall, so this is technically all over 1, right? And what I'm going to do now is what's called rationalizing the numerator. I don't know if you remember this from maybe your Algebra 2 class or something like that, maybe a trig class. So basically I'm going to multiply top and bottom by what's called the conjugate. So that just means the same terms, but now separated by the opposite sign. So now I'm going to add this. So like that on top, and then same thing on the bottom. So we do top and bottom just so that it's like 1, right? So we're multiplying by a factor of 1. And then the top simplifies nicely. So now we're going to get, so these come out of the square root, right? Because we're kind of just foiling here. So the first ones make a n plus 3. The middle ones make a negative times these two values. And then the positive on the outside cancel. So there's no like middle terms. And then at the end we get a minus n all over n plus 3 plus square root of n. Okay, and then the n and the minus n on here cancel, so that's good. Alright, so we end up with limit as n goes to infinity of 3 over, now on the bottom we have n plus 3, n plus a square root of n. Okay, so from this point, I can bring out the 3 in front, which, I mean, it doesn't really matter. You could keep it inside as well. I just like to do it because I like factoring things out for some reason. I don't know why. And then, so from here, when we plug in the infinities, 1 over infinity plus 3, I guess. The plus 3 is not going to matter. Plus infinity on the bottom. This is just going to be 0, right? So our limit is going to be, so I can just rewrite here. So our final conclusion is the limit, yes, the limit exists, and furthermore, it equals 0. Okay. All right, so that does it for that problem.